Sure.
Okay, hi everyone. I'm Katrina Manigan. I lead the Buildings and Homes team in Denver's Office of Climate Action, Sustainability, and Resiliency. Welcome to the first webinar in our new webinar library that we're making. I will pass things to Lucy to introduce today's webinar in a moment, but first I wanted to give you all just a little bit of context about all of our work on high performance buildings and homes. So Lucy, maybe do you want me to share my presentation? We're here today to talk about the Electrifying Multifamily Water Heat webinar, but just as a little bit of background information for all of you, I will just share a little bit about our work in general as context. So can you see my screen okay, Lucy?
Yeah, we can.
Wonderful. Okay, I'll tell you just 5 minutes about our work on high performance buildings and homes. This is the Denver Office of Climate Action, Sustainability, and Resiliency. We know that homes and buildings account for 64% of Denver's greenhouse gas emissions. And here are Denver's goals for buildings and homes. As a city, we've committed to eliminate greenhouse gas emissions by 2040. And so for buildings and homes, this means that all new buildings and homes will be net zero energy by 2030. All existing buildings and homes, net zero energy by 2040. We define net zero energy as highly efficient, all electric, grid flexible, and powered by 100% renewable electricity. And I want to go just a little bit into why we're talking about all electric buildings and homes as a little context and introduction for today's discussion about electric multifamily water heat. So first, renewable heating and cooling, or electrification, has really high impact climate benefits because we know that zero emission electricity is coming. We know that Denver's electric grid will be 80% renewable by 2030, and the city and county of Denver has a goal to be 100% renewable by 2030. And electrifying space and water heat, of course, reduces the demand for natural gas and moves the space and water heat onto this renewable electricity. And it also reduces methane emissions because there are methane emissions through methane leaks when natural gas is used, and methane is 80 times as potent a greenhouse gas as carbon dioxide. We know that by moving to renewable heating and cooling, we can get better outcomes, often for the same cost, even in existing buildings, but especially in new buildings. And you'll hear more about how that works for multifamily water heat today. And we know that electrification of space and water heat increases grid utilization, because Denver's electric system is already built to withstand high air conditioning load during the summer. Therefore, winter heating needs can shift to renewable electricity without significant infrastructure build out. Now, I just want to have one slide each on what we're doing around new buildings and around existing buildings here in Denver. So for new buildings, right now, the 2022 building code update is underway. And the chart on the right here shows the progression of various codes and how they compare to Denver's goal. So Denver has a goal, as I've mentioned, to have outcomes where buildings are performing at net zero energy by 2030. So then orange, you see the national, international energy conservation codes. In blue, you see the Denver Energy Code. The DEC 2019 is today's Denver Energy Code. It is 15% more efficient than the national IECC 2018 code. And the current Denver Energy Code for 2022 is the higher blue dot current status, and our code committees are going to be considering a whole series of amendments that have get us to this max potential dot that you see here, DECC 2022. So go and look at I'll put a link in the chat after I stop talking about the 2022 building code update, but a lot of decisions around what happens with our commercial energy code will be made over the next few months. Then with existing buildings, we have the Energize Denver program in place. We won't go into this today, but so you're aware of sort of one of the big work areas for existing buildings. It includes performance requirements for large buildings to improve energy performance 30% by 2030, and includes a renewable heating and cooling requirements for partial electrification of space and water heating systems upon system replacement when cost effective, starting in 2025. So you can go learn a lot more about all of our existing building work at denvergov.org/energizedenver. Lastly, I just want to mention we also have the Climate Protection Fund in place. These are the 6 allowable uses for those funds shown on your screen. And we will be developing a lot of incentives to support, especially the transition to electric space and water heat for existing buildings. We'll plan to develop incentives and supports for new buildings also, and look forward to engaging with all of you in how we can provide incentive dollars to help our community with this transition. I'll note that half of this funding is required to be spent to benefit under-resourced communities that are the most vulnerable to the impacts of climate change. So we'll be really focused on putting incentive dollars there. So with that, I'll pass things off to Lucy to kick off the webinar.
Awesome. Thanks, Katrina. Well, welcome everyone. I'm going to introduce myself. My name is Lucy Ehrencleugh, and I am the city's Existing Buildings Programs Administrator. And so this is our new webinar library. You can find this and other webinars, as well as additional resources and upcoming events on our webpage. We created this webinar library as a place where the community, industry professionals, and other stakeholders can learn, grow, and share ideas, all in support of Denver's mission to make buildings net zero emissions. You can register for upcoming events, watch past webinars, and view other resources by clicking the links that you see in this slide. We also welcome ideas and proposals for speakers, so feel free to submit your input to the suggest a webinar topic or request to speak at a webinar link on the webpage. I'll also go ahead and post that link in the chat when I'm done kind of introducing. So in this webinar, we will be taking more of a deep dive into electrifying water heating systems in new multifamily construction. Our speakers, Matt Abbott, Taylor Roberts, and Ryan Green, will cover successful case studies, overcoming challenges, and the financial and climate-related benefits of installing these systems in low and high-rise multifamily complexes. After our speakers present, we will then have time for Q&A, so go ahead and put your questions in the Q&A box or the chat to be answered at the end. All right, so to introduce our first speaker, Taylor Roberts has 10 years of experience in the building energy field. Taylor's focus is energy consulting with an emphasis on energy analysis and optimization. He is proficient in whole building energy analysis using OpenStudio and Energy Plus, and has provided energy design assistance for millions of square footage of commercial buildings. Now I'll go ahead and pass it off to Taylor.
Great, thanks, Lucy. Hopefully everyone can see my presentation. I'm gonna just kick things off and kind of go over some high-level opportunities that the heat pump domestic hot water heating affords for multifamily new construction here in Denver. So I wanted to start just kind of talking about the operating cost impact of electrification and some opportunities we've seen with new construction with this. So this slide really kind of shows some information from existing buildings. So this is some affordable housing around Colorado and information that we did from a study of electrifying these types of buildings. So typically, you know, low to mid-rise multifamily. You can see over there that all electric, near electric, and gas heating and the cost per square foot range from, with gas heating and domestic hot water heating, 77 cents, $1.14 for near electric, which is gas, domestic hot water, electric heating, and then 137 for all electric. The key thing to keep in mind here is that these all electric that was electric resistance domestic hot water heating, and typically a PTAC or a VTAC without low ambient heat pump operation. So pretty inefficient electric is what we would consider those systems. And you can see it obviously has a huge impact on that annual energy cost. Really, the main driver for that is that our demand charges with Xcel and other utilities in Colorado, but this is specifically Xcel. So when you have electric resistance, it's not very efficient and you get huge demand. You can see that for the electric buildings, about over 50% of the electric utility charge was demand charge, with 35% being use and then 6 being service. So that's a huge impact. And just in a BTU, looking at BTU per BTU, we can see that natural gas is about 6 times cheaper. So not a super rosy picture with those, but what we've seen is that if you take that all electric and you really make it efficient, so heat pumps, so we're going to talk about air source heat pumps today a lot for domestic hot water. So using those, using low ambient heat pump technology, using energy recovery opportunities for ventilation air, we can see that we can reduce that $1.37 a square foot and actually get it to where those gas buildings were closer to the 77 cents a square foot. So if you really make sure you're doing these things the right way and the efficient way, you're not going to have a huge energy penalty. If you do it really inefficiently, that's where we can see that big annual energy cost penalty from the utility. So saying that, there's also some really big opportunities, right? So the efficient system can get us to parity for annual energy cost. Usually there's some first cost there, but it can also provide cost savings and opportunities in Denver due to the Denver Energy Code and the Green Building Ordinance. So people that aren't familiar, Katrina kind of laid out where we are now and where we're going in the future for the Energy Code. But where we are now on the Energy Code, if you're using whole building compliance, which is very common for especially high-rise multifamily and then larger projects as well, you have to show 24% energy cost savings over the reference baseline. So pretty high amount of cost savings, right, or energy savings just to meet code. And then on top of that, you also need to comply with Green Building Ordinance. So there's a couple options in the Green Building Ordinance to use energy efficiency and leverage that for your compliance. So reduce green space, that reduces your green space requirement by about a third, and 5% savings over code. That's actually probably the most common pathway we see multifamily projects taking, but they've got to get to that 5% over code. So that'd be a total of 29% savings. And then the other option would be 12% savings over code. So full energy efficiency compliance with the GBO. That requires a total of 36% savings, right? The 12 plus the 14. So a bunch of percentages there, but basically what this means is the energy code for new construction multifamily is really hard. And when you go electrification of domestic hot water, it opens a huge opportunity for increased savings to use these pathways. So for new construction, we typically see domestic hot water is about 15 to 20% of the annual use and cost of the building. So a huge chunk, right? And that's using gas or electric resistance, assuming. So going to heat pump water heaters, your average COP might be somewhere between 3 to 2 over the year, depending on how that heat pump water heater is operating and when it can operate and down to what temperatures, et cetera. But so that savings could be up to 10% or even more, right? Just one measure going to heat pump water heating, you can get 10% savings for your building. So it's it's one of the most impactful measures you can do to save energy for your energy code compliance and meeting the Green Building Ordinance. And to kind of explain that, I have an example here. So this is just a generic multifamily 100,000 square foot mid-rise project, right? So really common building size and type in Denver. If you look at the chart on the right over there, that's the end use breakdown of the projected annual utility cost. So we can see again, water heating, for this specific project, it's about 30%. So 29% of that annual utility cost is coming from domestic hot water. So it's actually the biggest end use of everything in the building. So a huge end use. And the reason for that again is because for this specific project, it's using electric resistance individual water heaters. So an individual water heater per unit with electric resistance. Again, not a very efficient way to do it. And that's what leads to that huge orange section of the pie over there, which is the domestic hot water. It is using pretty good heating, split DX heat pumps with low ambient heat pump operation, has good glazing envelope, LED lighting. So this is kind of a typical, project that can meet that 20, they were right at that 24%. So just hitting energy code and being all electric, right? So, but just hitting code, they still have to meet the green building ordinance on top of that, right? So they have another layer of what they have to meet for permitting. If replacing those individual water heaters with a central air source heat pump water heater resulted in another 14% energy cost savings. So it took them from 24 to 38%. So just that one measure would comply with the green building ordinance. So now they could go the energy efficiency pathway on the green building ordinance and have no green space requirements. So a large cost savings there on the green building ordinance implication, and just really providing huge savings for the project, right? There's the possibility of doing that with individual as well. Individual has its own complications, as does central. But for this specific example, it was the central air source. And again, just that one measure gave them compliance with GBO. So or could give them compliance with GBO. So that's really the big takeaway of that for the energy code savings. The last thing I wanted to touch on is rebates opportunities for heat pump water heaters. So there aren't any specific ones for a commercial building going to Excel's EDA program, but the Energy Design Assistance EDA for Excel provides incentives for anything that saves energy in a building, right? So heat pump water heaters definitely fall under that. So rebates are calculated based on the kW, kilowatt hours, and therms, right? Therms don't apply for this, but the kW and kilowatt hours for electric buildings compared to that baseline design. So when we go to a heat pump water heater, that heat pump water heater gets compared to an electric resistance water heater in the baseline. So all those efficiency savings of having the COP of using that heat pump result in an incentive impact. That's pretty significant. So on a project, this is actually in Boulder, but it's about a 300,000 square foot multifamily low rise actually in Boulder. The incentive just for the heat pump water heaters was about $77,000. So again, it's not going to pay for the heat pump water heaters, but there's definitely incentive out there that increases and can offset some of that cost. And again, that was from the KW and KWH, mostly kilowatt hours saved from the heat pump water heaters, which was significant and added to that overall, or added 77,000 to the overall utility incentive. EDA is only for, larger 50,000 square feet or more buildings. I believe Excel does have some prescriptive rebates for heat pump water heaters, but this specific example is, leveraging Excel's whole building analysis rebate for specifically heat pump water heaters. And yeah, that's really all I had. So I'll stop sharing and hand it over. But again, kind of the big examples, right? Heat pump water heaters can provide significant savings for an electrified building on the domestic hot water side for multifamily. It really helps with energy code compliance, with GBO compliance, And also through Excel's Energy Design Assistance Program, the incentive will be significantly increased utilizing the heat pump water heaters.
Great. Well, thank you so much, Taylor. Our next speaker, Matt Abbott, is a development manager at Alta Terra Real Estate. He recently left Give Group, where he split his time between data collection and case studies for an open source program and research and development efforts for HVAC, water heating, and supply chain. Matt manages numerous partner relationships related to electrification and regional air quality. I'll hand it off to you, Matt.
All right, just getting the screen sharing going. I'm seeing some hazard things on mine. 1 second. Just have to authenticate this. It's a new computer to me. Should be good to go now. All right, so I'm Matt Abbott. Thanks for the introduction, Lucy.
Matt, real quick, we just see your note slides. Not
okay, let me switch that up. Yep.
Thanks.
Thanks for catching that. How does that look?
Still on the note slides.
I think in the upper left-hand corner, Matt, it says swap displays. Try.
How's
There we
that?
go.
There we go.
Perfect. Thanks for coaching me through that. Apologies for the delay. So I'm a generalist and a developer. I'm not an engineer like the rest of the folks here. And I'm going to run you through kind of what Give did. And I'm sure I'll say we a lot of times, which will be confusing. But I am now working for Alta Terra, as mentioned, and we're taking the same theory to 6 states, so outside of Utah. But I'll just run through the Give hypothesis for the most part. So Salt Lake City has an air quality problem, and that was Give's motivation for going all electric. There's a lot of secondary benefits that came from that, but are basin-like geology and geography compounded with vehicle emissions and then building emissions. And we switched to mostly having issues with building emissions the next couple of years. And that's because cars are replaced more frequently than buildings. And their technology is improving more quickly. So we focused on the tailpipes of buildings and figuring out how we can transition away from traditional building technologies towards all electric. The first project was Project Open 1 in 2017, and we have iterative versions of the approach to all electric. And Give specialties LIHTC or low-income housing tax credit projects. So urban infill, deeply affordable, and that kind of sets the pace and the motivation for each project. And we build in Salt Lake, Ogden, and Provo. So similar environments to Denver. And there's a lot of evidence that these technologies can be applied throughout the state of Utah. So it should be throughout the state of Colorado. Though you guys do have a few cities that are a little higher than ours. And it's all made possible with very close partnerships with our architects, engineers, GCs, et cetera. In particular, the architect and engineers for the design phase, and then a lot of willingness to jump on the learning curve with our GC. Why this is important is because this has become lines of business for each of those architects, engineers, and GCs. They've sold a lot more buildings than what they did for Give as they've adapted to these technologies, figured out how to improve them and sell them. So, building scales larger than what Give was executing. The specific technologies are pretty familiar. It's heat pump, hybrid heat pump, and then every building is solar PV, battery, and EV ready. And there's a few sites where we've executed on all 3. The important thing to note here is that some of these problems are harder than others, and they have different incentive systems. And the specific one, which is the topic today, is domestic hot water. That's been our big challenge, the most iterations, the most change across our building types. And this is Project Open 1 in the photo here. So the big win is the first cost perspective for all electric. We're coming out 1.1% cheaper with fully paid for plan sets and bid packages on traditional building and all electric. So that's well evidenced at this point. And our utility incentive on this most recent project was huge. I don't think it's a totally typical incentive, but it was 344,000 for an 80-door project, which was a big chunk of change. And we're regularly seeing tenant costs at $55 or below. And the $55 is anchored on our least efficient project. We've just gotten more efficient as time goes on. And there's excellent evidence from University of Utah that O&M for the life cycle of the building is significantly cheaper for all electric. They did a very conservative study on multifamily, commercial, and clinic space to assess this. Clinic space is really tough to do all electric, but everything else, it's at parity or cheaper at this point. And then, like the big selling point is one less utility on site and a reduction of sub time. So not having all the natural gas infrastructure going into a building is a substantial time saving, space saving, management costs, headache elimination. And we're saving around 12 square feet per unit, which works out for more units or more space in the building or a tighter building. The obstacles are learning curve primarily. It's being willing to kind of take the hits over time, to learn, to adapt, is a challenging mindset for a developer. We really want to hit our pro formas, get in there, get out of there, and move on. So adapting this iterative mindset was kind of a cultural shift. And then within that, there's the amps per unit. Our first project, we're pushing a ton of copper. It was challenging for our GC, and it was mostly related to domestic hot water. And then finally, there's kind of the belt and suspenders mindset. If you're trying something new, you try to make sure it doesn't fail, because failure is very costly. So we have some over-engineered buildings that over time we're more confident with certain technologies. So this is kind of like the thesis. This could be the whole presentation right here. It shows the cost per unit for two different water heater technologies. We started off with on-demand electric, which is a very bad idea. And then we've moved towards centralized hybrid heat pump water heaters. And these are the specific units that are on demand. They have two 40 amp poles. They use a ton of juice. They also build up mineral deposits. We have hard water, like I believe you all do. But they were successful from a maintenance and operations perspective. So tenants were happy, and we're still getting relatively low hot water bills. But it circles back to those demand charges if they're centralized. But for the case of Utah, each residential unit has a separate meter, so there's no demand charge. Where we've migrated is centralized domestic hot water heat pumps. So 4 units in parallel, and you kind of see it here for Pamela's place, and it's the same basic design in Citizens West, which is our most recent. So it's 4 units in parallel. The rooms are operated as outdoor space, which is kind of tricky in some ways with louvers. So the weatherization, air sealing, all of that is a little extra work, and in good coordination with your GC. And then we do think there's a waste cooling opportunity because you're generating a lot of cooled air, along with better louver programming, but we just haven't gotten there yet. So the basic system works effectively where they're sub-metered and billed per tenant. Costs are low, operations have been straightforward, no complaints about water heating, hot water access. So the recircs work just fine. So engineering wise, it's all working out. And then, as we've been assessing this technology, looking forward is the, someday it'd be great to get to more of the swing tank structure. This has been demonstrated and in full operation in the Pacific Northwest with Bonneville Power, specifically using CO2 heat pumps. The CO2 heat pumps do best with a high delta T, so very cold water coming in. And you can use fewer of these heat pumps per floor because they generate higher outputs for hot water as well. So you can mix down or just have a centralized tank that's at higher temperature. So this is where we're exploring. None of them were deployed. We have a lot more of these deployed right now than this technology, but just wanted to paint the picture of where we're thinking. Happy to answer any questions at the end of the presentations. And then there are my contact details along with GIFs. So happy to connect anyone to GIF or share our resources from GC architect engineering perspective.
Awesome. Thank you so much, Matt. Our final speaker, Ryan Green, currently works at Nyle Water Heating Systems as the Director of Strategic Accounts, where he leads the heat pump water heater development. He was formerly at Shark Energy Systems and has been in the HVAC and energy efficiency manufacturing industry for over 11 years. Now I'll pass it on to you, Ryan.
Thank you, Lucy. So yeah, we're a manufacturer of commercial heat pump water heaters, primarily large central systems. And let me get my screen shared here. Hopefully everybody can see that.
Yes, we can see it.
Awesome. So, there's been, Matt touched on it a little bit, there's been a really big emergence, particularly up Pacific Northwest, of decarbonizing domestic hot water using centralized heat pump water heating systems. There's a group named the Advanced Water Heating Initiative. I recommend anybody who's listening into this to take note of that group and to, take a look at what they're doing as far as advancing the heat pump water heating industry as a whole. They have a specification guide that's very useful as far as how to apply these on a residential scale as well as a large multifamily scale, piping diagrams, guidelines, sizing guidelines, all kinds of different things. Because let's face it, when we're talking about heat pump water heaters, change is pretty confusing. It's a different way of doing this. There's lots of different topics that we're talking about. There's usually an increased storage volume that's being talked about. So we're going from hearing about instantaneous water heaters that don't have a lot of storage to heat pumps that have to have a lot of storage. Minimum outdoor air temperatures start becoming a topic of the conversation because now, heat pumps vary their capacity based on what type of source temperature they have. There's different piping diagrams or piping methodologies. Matt touched on that single pass methodology of how do you maintain stratification in tanks. There's just in general a lot of questions going on out there. So, we're really happy to be a part of this industry. We've been doing heat pump water heaters for over 13 years. We brought a lot of different applications and knowledge from different markets. We've been applying this and really starting to see this start getting into the colder climates as heat pumps get more advanced. So yeah, what are we seeing out there? Seattle, Denver, New York, all of you guys are doing different things in different paths to get to the same decarbonization goal. Seattle and New York, they've banned natural gas. Seattle's new energy code, any building over 25,000 square feet has to use a heat pump water heater. No electric resistance except for a small amount for the recirculation loop losses, and no fossil fuel for water heating in any of those buildings either. Additionally, they've added a little perk in there for if you do a low GWP, which Matt was talking about, there's low GWP refrigerants nowadays where you can do CO2, which is one, or other different refrigerants. They added a little kicker in there to get extra points if you're going advanced on the refrigerant systems too. So the big thing is that, again, there's a lot of things changing out there, but the good news is there's a lot of other areas that have either outright banned or their codes are saying, hey, you have to use heat pump water heaters. So there's been a lot of things of learning how they're applying it there that can really be applied across a broad swath of buildings across the US. Taylor touched a little bit on this, but one thing I really wanted to break out is when you're looking at your domestic hot water load, there really is two primary loads that we're looking at. You got the primary domestic hot water load of the building of being able to have enough hot water to meet in a multifamily that peak demand in the morning. And then you also have the building recirculation losses. So even in a low demand time, you have that building recirculation pump running, and depending on the level of insulation on those recirculation, that amount of energy loss can be sometimes up to 3 kBtu per square foot, which is a very large amount of energy loss just associated to something that is in a multifamily building. Denver, a brief profile on that. We've, from the CSR reports, 90%, 96% single family low rise are individual gas. And then once you start getting up to the mid and high rise, you start going to these centralized systems. So having the ability to have a large central system that operates like a central gas domestic hot water plant is really starting to be where heat pumps are going to. So real briefly on heat pumps, these large central systems, two methodologies. No matter what, we're taking heat from one source, moving it into a refrigerant loop, and then moving it over to a condenser and transferring it into a potable hot water loop. Those sources are either air or water. So air source heat pumps, as we've kind of already talked about, they're extracting energy from the surrounding air. If they're put in a mechanical room, it's that air in the mechanical room, or if they're put out outdoors, it's that surrounding air. So that's where that topic of how cold can we get down to with an air source heat pump starts to be part of that conversation. Water source units present another code opportunity as well, because also in most of the IECC codes, there's points for heat recovery. And water source heat pump water heaters are just that. If you've got condenser water, chilled water, any of those two types of waters flowing around a building already, you already have a convenient heat source that can be tied into with a heat pump water heater to begin making all electric domestic hot water for that building. Out in the market, residentially wise, we're seeing really three different types of heat pump water heaters being applied. Hybrid tank style, already kind of been touched upon. You've got the heat pump right on top of the tank. Usually if it's an indoor space, you're ducting that out. There are also split system residential systems where you have a small little heat pump that ties into any traditional electric or gas water heater and then acts as that heat pump next to it where you're not having the tank and the heat pump as one unit. And then there's also CO2 split systems where you're having the heat pump just like a mini split. It sits outdoors and then pipes into a tank indoors. On the commercial level, more of it, or not more of it, all of the systems that we see out there are all split system. Again, we're going to a large central plant and then piping into tanks and then distributing that hot water out to the building. We've seen there's split systems for traditional refrigerants and there's air source and water source split systems for CO2. So really there's lots of different options out there for commercial heat pump water heating, which I think is a really exciting thing. I was just out at the AHR Expo a couple of weeks ago, and I have to say heat pumps and heat pump water heaters were really the theme going on. There's lots of new players entering the market. There's lots of new technology changes going on. So I think that's what's really exciting about the space in general is it's starting to get more crowded and a rising tide raises all ships and helps everybody get to this decarbonization goal. So one real quick thing to kind of note with this is heat pumps are not boilers. So gas water heaters, you can oversize them. They've got an instantaneous output. They can do lots of different modulating options. The outside air temperature doesn't really affect its performance. And for the most part, it's a really plug and play, easy, very understood system. Everybody's used to it. So when we switch over to heat pumps, it's really the exact opposite mentality. Oversizing gets extremely expensive because compressors are much more expensive than a gas heat exchanger. It really requires the right sizing of those two loads I was discussing. The domestic hot water plant usually gets a little bit bigger. The controls are a little bit more complex, and there's different refrigerants for different applications. So there's all different things that are starting to be considered that were never really once considered with the gas systems. One thing I will touch on that I know Taylor and Matt have also touched on is electric resistance, especially with Colorado's current dirty grid, really a bad move. So, if you're looking at the greenhouse gas emissions, if we were to switch over to the lifespan of a electric water heater, you're looking at over 10 million pounds of CO2 generated versus a natural gas boiler that would be emitting about 3 million. So a direct swap over to electric resistance is literally shooting ourselves in the foot at this point. So that's why heat pump water heaters really, as Taylor touched upon, have a very tremendous opportunity to bring down that overall energy use intensity and improve the efficiency of that building. So out there, how are we seeing this applied in all electric multifamily buildings, medium to high rise type applications? When we get up in larger high rise, the most popular choice that we've seen out there is a water source heat pump loop. So they've got condenser water flowing around to water source heat pumps on all the floors. And now instead of using a gas boiler and a cooling tower as their heat rejector and heat injector, they're using a reversible air source heat pump that can operate at lower ambient temperatures just to maintain the temperature of that condenser water loop at their summer and winter months. So now what is done is a water source heat pump water heater ties into that condenser water loop. So in the wintertime, you're having to add a little bit more heat because you're extracting some from that loop. But in the summertime, you've actually got an economizer. So you're having to reject less energy out because you're pulling some of that energy just to make domestic hot water for it. So there's a lot of energy trade-offs that you can get from these water storage systems. Additionally, if you've got a chilled water building, 4-pipe fan coils going around, an air source heat pump is used for the hot water side. Cooling tower is your heat rejector. And then off of the chilled water return, you could put in a heat pump water heater that's pulling energy off that chilled water return and providing that domestic hot water for that building. And again, you've got a 4-pipe chilled water, hot water, all electric building for multifamily example. What we see a lot of, tremendous amount of projects, especially Pacific Northwest, climate lends to it, but we also have a lot of air-cooled VRF projects here in Denver. And what we're seeing in cold climates is they'll do the air-cooled VRF systems or PTAC or a VTAC, and then the heat pump water heater system, they'll put them in the parking garage, where parking garages are a little bit insulated from the outdoor air temperatures. So you can extract that energy from the same floor or bottom or lower floor parking garage, pull that heat energy from there, and then duct the central heat pump water heater out of that space so you're not overcooling it, and be able to get a much better performing heat pump water heater in colder climates where you're not having to put it outdoors. This was an example really of just that. You can see these are in an indoor mechanical room. The heat pumps themselves are ducted out of that space. If you look carefully on the left picture, you can see the grates in the ceiling. So that's where the parking structure is actually right above the heat pump central plant. So anytime those heat pumps are operating, they're pulling that warmer air from the parking garage to use as the heat source. And then you can see the duct coming out of the unit that gets ducted directly out through a louver on the building. So they're able to have that central heat pump system maintained at a minimum of about 40-45 degrees all year round. And this is actually in Vancouver. So they're getting much colder temperatures than that 30, 40, 50 degrees, but they're able to maintain it because it's in that insulated parking structure. This was a water source example. They had chilled water flowing around the building. We were able to just pull the chilled water, use that as the source, and then create the domestic hot water. Another thing that comes up a lot, space considerations. This was an example of a project going up I think it was also in Vancouver, another example of where we're pulling air from the parking garage. So that green square is actually the sub-level, P level 2. This is P level 1. So we're pulling the energy up from that P level 2. And then there's ductwork coming off those heat pumps going into the central exhaust air shaft. So again, they're minimizing the impact of that outdoor air by using the insulated, more warmer air from the parking garage, and then being able to produce domestic hot water and not that large of a space for a very large building. This is 219 units, 575 total occupants. We're producing over 17,000 gallons of domestic hot water a day. So it really doesn't have to be a giant, the big thing is, we need a whole bunch of storage tanks. You can see there's almost 2,500 gallons or almost 3,000 gallons of storage with 4 750-gallon tanks. A small electric resistance backup, which is that swing tank methodology where that electric resistance is just heating the recirculation loop. And then the domestic hot water central plant is really made to, when everybody gets up 6 to 9 a.m. showers, those tanks drain down. Additionally, we've seen the heat pumps put on a roof, hybridized with gas water heaters, internal storage tanks. This was a much larger occupancy building. You can see about 1,222 total occupants. So the other thing that we talked about on this project was actually moving it over to water source. You can see the cooling towers are there. So condenser water could have been an option here as well. Katrina touched upon this a little bit of, grid flexible, all electric devices. So heat pump water heaters are just that. As everybody's electrified, we've seen that, it's good, but the problem is a lot of these devices are uncontrolled and we're seeing these random peaks across. So heat pump water heaters, especially when you get a larger amount of in a space, those loads can actually be aggregated. And as they've touched upon, especially in areas with large demand charges, that's worth dollars per kilowatt. And these types of devices, they already come with a DOE regulated, it's called a CTA 2045 or Eco Port. And that allows the utilities to do just that. So all heat pump water heaters have this port in it to where the utility can already tie in and say, hey, we've got a peak demand event coming up. Don't run the compressors or increase the storage temperature from 140 to 160. and start doing these things that allow this heat pump water heater to be that grid flexible device that allows it to have that building start interacting with the grid using its domestic hot water system. Thank you very much. Open this up for questions and unshare this.
Awesome. Thank you so much, Ryan, and thank you to our other speakers as well. We have one question in the Q&A, and it says, why are high-rise EUIs significantly higher than low-rise construction? Is it primarily due to pumping water / condensate, et cetera, throughout the building?
Primarily the increased just overall square footage of those buildings. And most of the time in those buildings, the HVAC systems deployed, just the overall energy use of them increases primarily square footage, but also the age of HVAC systems. That data was taken from existing buildings as well. So age of HVAC systems increase the energy use as you have increased square footage, because that the EUI is kBTU per square foot per year. So as that square foot goes up, you can see an increased energy use intensity.
Yeah, Ryan,
Taylor, you might have some comments too.
Yeah, a few things we see just specifically for Denver too that leads to that. One would be a lot of times high-rise buildings are providing ventilation, so they have 24/7 ventilation to the units. So that's a heating load that may be low-rise. They might just be doing natural ventilation, which is really no ventilation. So there's a heating load differential there. Also amenities, so a pool that has a huge energy use, and that's something too, I think kind of the next phase two of looking at using heat pump water heaters technology for pool heating. But that's a huge energy use that can lead to that. So there's some just different, type issues that the larger high-rise buildings have that can lead to that higher UI.
Awesome. All right, another question. The building I currently live in has a gas-fired boiler that provides both heating system, water, and domestic water. The boiler is at end of life and requires replacement. When the system is replaced, should we separate the domestic and heating water systems and have domestic hot water provided by a heat pump, but have the building heating system water provided through a gas-fired boiler? And then in follow-up, in summer, when we are cooling, the water is switched over to a chilled water source to provide air conditioning to the same fan coil units that chill the air in the individual units.
So Ryan, I'm not sure if you have an answer, but so that's like an aquatherm system,
Yep.
is pretty common. I do know there are some heat pump technology or air source heat pump technologies that kind of can do what you're talking about, which would be heating and also providing chilled water, so reversible for that fan coil. We haven't seen any implemented in projects. It's still pretty new technology. I think Ryan might have some more information on that. So commonly right now, we do see that split where, like, if you have an aquatherm, you have a condenser on the roof and a split DX cooling, you could make that a heat pump and then go to a heat pump water heater. You'd have two heat pumps essentially for that. So.
And then if it was like a gas central system, because I've seen that too, where they've got a gas boiler going over to like an indirect tank, that would be another opportunity where you could do a heat pump water heater or an air source heat pump going out over an indirect tank too. So really kind of just depends on where that gas boiler is. If it's in the individual units, it would be more of an approach like Taylor said. If it's more of a centralized, then it would be more of a central heat pump water heater type.
Can you touch on smaller scale multifamily projects where individual water heaters are the norm? What resources can we point engineers towards for design and installation requirements as far as space and venting requirements, impacts to space loads, et cetera?
Matt, I think that's all you.
I'm assuming smaller scale, you're kind of thinking more like townhouse 3 to 5 as opposed to 70, 80 plus. We did run some projects off of where we had 2 or 3 units on one, so that's possible. I don't have Colorado requirements, but I'm happy to put, I know that there's some people signed in under multiple names, whoever this is under Elizabeth Gilmore's name, in touch with our engineers and our architects, and then give shares all their building plans. So if there's anything you're trying to point them to as an example and then adapt to local code, all those resources I'm happy to connect you to. So feel free to reach out.
Yeah, I would just add to that, we've done projects with individual and also projects that have done like what Matt was saying, which is more have a couple heat pump water heaters serving several units. That seemed to be better from like a space requirement because they are bigger. And then Elizabeth, all I would say is when we did the analysis on all the different ways you could duct the heat pump water heaters, if you're bringing in outside air, if you're pulling air from the corridor, if you're pulling air from the space, and then where you're ducting that cold air, it seemed like some of the better solutions were, like what Matt had, which was more of like a mechanical room, or pulling from, like a non-continuously occupied space, like a corridor, or even if pulling from the space, doing that, but then making sure you're ducting that cold air somewhere else. So it's not the comfort issue.
And I think I'll add to that too. I think there's actually something in the incoming IECC 2021 specifically related to putting heat pump water heaters in conditioned spaces that it kind of disallows that, especially in colder climates, that you don't want to have that energy penalty from, basically cooling the space off. I think there's something in the code on that as well.
All right, can you also touch on building electrification for multifamily? What does it take to change a multifamily project with individual hot heat water heating to a heat pump with regard to space requirements, venting, and impact on local HVAC loads?
I think we partially covered that. So, and I'll definitely let the more talented technical folks expand on this. Retrofits are challenging, and it's mostly from a panel capacity perspective, at least from what I've run into. The space requirements we have for HVAC within our units, we manage most of the HVAC within a cassette above the bathroom space. So we tend to see net savings in space. Ventilation, as we touched on earlier, is a constant thing. If you're not managing ventilation is still happening. You don't get to choose where the air comes from. So that's an air quality problem, and that can be a temperature or comfort problem as well. So I would recommend targeting outdoor spaces or having vents or chases that manage it as such. But yeah, retrofits are challenging. I think if the project's in design or under design, you just need a talented engineering group to kind of look through that and figure out how to accomplish this.
I think Elizabeth just specified that question is with respect to existing buildings as well. All right, awesome.
I think, Elizabeth, and looking for that one-stop resource, I think we're all looking for that. And I think existing buildings, and even new construction with individual natural gas water heaters, it could be a huge risk for the building with Energize Denver and the requirements. I don't know how you would retrofit it with an individual heat pump water heater and be able to duct it appropriately, and if it even fit, because they're typically bigger. So I think it is a huge risk, and you might have to try to utilize some other space in the build, I don't know. I think it's going to be a nightmare, honestly. So being able to not do that right now, I think makes a lot of sense for buildings. And then existing buildings, I think it's going to be, trying to get some good case studies and some good examples of how people can do it to help the design community.
Let's watch what New York does. I was in a similar conversation with them the other day. They're like, yeah, you realize our retrofit building stock is a little bigger than our new stock. And it's like, yeah. So I think New York could be a really good case study project to watch it in terms of retrofit with all the low income and the X building out there. And it's going to be a really good opportunity for kind of taking a look at how they're going to do it.
All right, another question. This one's for you, Ryan. Have you seen any projects with a shared outdoor condenser shared for both domestic hot water heating and space heating?
I have not, and the primary reason is the two, one is a potable load and one is a non-potable load. So, I mean, if you had it, you could do it, you would just have to have a separate heat exchanger that's decoupling those. So you're not having any type of contamination with the potable water.
We also went through a design exercise on this, and we're running into inefficiencies with recirculation for like a hydronic system.
Yeah.
All right, anyone else have any more questions? All right, great. Well, we can wrap this up a few minutes early and everyone can get 5 minutes more of their day back. So I wanted to thank our speakers and also all of our attendees for coming and joining us today. Thank you guys so much. We really appreciate it. And don't forget to check that webinar library page for this recording in a little bit, and then also for past recordings, the survey for upcoming topics and speakers, and have a great rest of your day.
Thank you.